The field of fluid mechanics is concerned with both fluid dynamics and hydrostatics. Fluid dynamics looks at fluids in motion and studies the forces produced by the fluid on objects that are immersed within it. In contrast, hydrostatics deals with fluids at rest and equilibrium. Fluids can be categorized as either a gas or liquid. Gases expand to fill their containers, yet are easily compressed. Liquids take the shape of their container, typically leaving a free surface, and require effort to compress. Some important properties of fluids are its density, specific volume, specific gravity, bulk modulus, compressibility, viscosity, and kinematic viscosity. These properties are functions of variables such as temperature T and pressure P. Whether the fluid under consideration as a gas or liquid also affects the temperature and pressure dependence of its properties, since the interactions occurring at the molecular level are different for a gas and liquid. Density is defined as mass per unit volume. Here, m is mass with units of kilograms, v is volume with units of meters cubed, and rho is density with units of kilograms per meter cubed. As the mass in unit volume increases, so does its density. A few examples of different material densities are that of air, with a density of 1.29 kilograms per meter cubed, water with a density of 999.8 kilograms per meter cubed, and lead with a density of 11,340 kilograms per meter cubed. These measurements for density were taken at standard temperature and pressure, or STP for short. At STP, the temperature and pressure of the surrounding environment are 273.15 Kelvin, or 0 degrees Celsius, for temperature, and 101.3 kilopascals, or 1 atmosphere, for pressure. What the temperature and pressure are is important, because density is actually a function of both. Take water, for example. Water is very unique because its density is a complex function of temperature. If we hold pressure constant at 1 atmosphere, we see that it has a maximum density at 0 degrees Celsius. At very low temperatures below 0 degrees Celsius, water freezes into ice, and its density decreases the lower its temperature gets. For temperatures greater than 0 degrees Celsius, as the temperature increases, the density of water decreases as well. In general, the density of water is insensitive to changes in temperature. There is only about a 5% difference in its density from 0 degrees Celsius to 100 degrees Celsius. The temperature dependence of density for air is less complicated. As temperature increases, density decreases. However, the decrease in density is much more dramatic for air than it is for water. There is a 21% decrease in density, going from negative 25 degrees Celsius to 45 degrees Celsius. Here, the difference in the temperature dependence of density for a gas and a liquid is evident. The density for gases is much more sensitive to temperature than for liquids. Specific volume is the reciprocal of density. Here, nu is specific volume. It has SI units of meters cubed per kilogram. Providing a new variable for the reciprocal of density will be useful in the future because it reduces the complexity of formulas. Specific gravity has two definitions, depending on whether the material under study is a liquid or a gas. For liquids, the specific gravity is the ratio of the density of the liquid being studied to the density of water at a given temperature and pressure. For gases, the specific gravity is the ratio of the density of the gas being studied to the density of air at a given temperature and pressure. We will see later that when the specific gravity of a fluid is greater than 1, the gas or liquid will sink, while the reference material, air or water, will rise. Additionally, air and water are not always used as the reference. Other materials can serve as a reference. When using specific gravity, it is important to know what the reference material is, as well as the temperature and pressure when the reference material's density was measured, because the temperature and pressure must be the same when measuring the density of the material of interest. The bulk modulus of a material is defined as the ratio of the change in pressure to the change in volume per initial volume. Here, K is the bulk modulus with SI units of pascals, dP is the change in pressure, dV is the change in volume, and V initial is the initial volume before deformation. To better understand this, let's take an infinitesimal cubic element of a fluid. This element is experiencing forces on all of its faces as a result of the pressure in the local environment. At the moment, the element is in equilibrium, but if the pressure in the environment increases, then the forces exerted on the faces of the element will increase as well. These increased forces will result in the compression of the element. The bulk modulus provides a measure of the resistance to compression by the element. Bulk modulus is an important property of a fluid because it determines the speed that sound can travel through the material. The higher the bulk modulus, the more resistant the material is to compression, and this allows sound waves to be propagated through the material faster. The speed of sound in a liquid can be calculated as the square root of the ratio of the bulk modulus to density, where c is the speed of sound, k is the bulk modulus, and rho is the density of the liquid. Knowing how to calculate the speed of sound will be important later when considering the Mach number. Finally, the reciprocal of bulk modulus gives the compressibility of the material. Beta equals 1 by k, where beta is the compressibility with units of pascals to the -1 power. Fluid flows can be characterized as either turbulent or laminar flow. Laminar flow is when the fluid particles flow in an orderly manner along the direction of flow, and their movement perpendicular to the flow is limited. When a liquid like water has laminar flow, it looks like glass. Laminar flow occurs when the Reynolds number of a fluid is adequately low. However, if the velocity of the fluid or the dimensions of the geometry the fluid is flowing through changes, then this can increase the Reynolds number above a certain threshold and cause the fluid to transition from laminar flow to turbulent flow. In a turbulent flow, the fluid particles can move with, against, and perpendicular to the flow. Here we can see that the fluid at the top has a laminar flow, but downstream it transitions to a turbulent flow. A first step to understanding how fluids behave is to create a mathematical model relating important measurable quantities of the fluid. Two important quantities of fluids are shear stresses and its velocity gradient. But first, what is shear stress, and what is a velocity gradient? To understand shear stress, let's look at an infinitesimal cubic element of a fluid. When a force is applied parallel to any face of the cube, in this example it's the top face, it results in a shear stress over that face. Shear stress is defined as a force divided by area. Here, tau is shear stress with units of newtons per meter squared, or equivalently pascals. F is force, and A is area. One more important thing that must be mentioned about shear stress concerns the direction the stress acts in. This is indicated by two indices on the symbol used to denote stress. The first index indicates the face on the element the stress acts on. The second index indicates the direction the stress acts in. In this example, the stress acting on the element would be expressed as tau sub yx. The first index is y because the stress acts on the face with a normal vector pointing in the positive y direction. The second index is x because the shear stress is acting in the positive x direction. Shear stresses are indicated in figures by half arrow pointing in the direction the stress is acting in. Shear stress is what gives a fluid the characteristic of thickness by providing a resistance to fluid flow. To understand what a velocity gradient is, let's look at two layers of fluid particles. When a fluid flows, these layers move relative to each other with different velocities. The velocity gradient is the difference in these two velocities divided by the distance between the two layers. This quotient can also be expressed as the derivative du by dy. Sometimes the velocity gradient is also referred to as the shear rate. Now that we know what the shear stress and velocity gradients are, how do we determine the relation between the two? To do this, experiments must be performed on the particular fluid of interest, and both quantities measured. By plotting both of these quantities, a mathematical relationship can be established. One of the ways to measure these quantities of a fluid is to use an instrument called a shear rheometer. The fluid of interest is placed between two geometries, which can be flat plates, cones, or other shapes. The surfaces of the geometries can also be smooth or rough. Here, a shear rheometer using two smooth flat plates is shown. Then, depending on the type of shear rheometer, the fluid is then subjected to a shear strain and the resulting shear stress is measured, or the fluid is subjected to a shear stress and the resulting shear strain is measured. This is typically done by rotating the top plate that the fluid is in contact with. The layers of fluid in contact with the plates are stuck to the plates and move at the same speed as them. This is known as the no-slip boundary condition. The type of flow produced by the rheometer is known as a shear flow. In a shear flow, the fluid is assumed to move only parallel to the plates, and the velocity of the fluid increases perpendicular to the flow of the fluid. After taking several measurements from the rheometer, a graph showing shear stress to velocity gradient can then be made from the measured values. Different classes of fluids exhibit different types of behaviors. When the relationship between shear stress and velocity gradient is linear, then the fluid is known as a Newtonian fluid. This can be modeled mathematically using the equation for a line, y equals mx plus b. Here, y is the shear stress, x is the velocity gradient, and b is set to 0 since there is no offset. With these substitutions, the following equation results. Tau equals m times du by dy. Here, m, the slope of the line, is a property of the fluid being investigated. This property relating shear stress and velocity gradient is the dynamic viscosity, also known as the coefficient of viscosity, and represented by mu. Substituting mu into the model results in what is known as Newton's law of viscosity. Tau equals mu times du by dy. Plotting shear stress to velocity gradient for different Newtonian fluids will show that the slope will be different depending on the fluid investigated. There are fluids, however, that do not have a linear relationship between shear stress and velocity gradient and are called non-Newtonian fluids. These non-Newtonian fluids have their own constitutive relationships. The first of these is called an inviscid fluid. Inviscid fluids are fluids that experience no shear stresses despite having velocity gradients. They are also known as superfluids. An example of an inviscid fluid is liquid helium once it is cooled to 2.17 Kelvin at 1 atmosphere. Another non-Newtonian fluid is a Bingham plastic. Bingham plastics do not begin to flow until the shear stress applied to it equals the yield stress, tau naught. Once the yield stress is reached, the relation between shear stress and velocity gradient is linear. The last example is called a pseudoplastic fluid. The shear stress to velocity gradient relationship for a pseudoplastic fluid is nonlinear. As the shear stress applied to the fluid increases, the viscosity of the fluid decreases. This is described as shear thinning. Now that we know what dynamic viscosity is, let us define kinematic viscosity. Kinematic viscosity is the ratio of dynamic viscosity to density, with SI units of meters squared per second. Here, nu is kinematic viscosity. Kinematic viscosity is useful since this ratio appears frequently in equations. Let's see how we can use Newton's law of viscosity to find the shear stress throughout a fluid in a Couette flow. Water, a Newtonian fluid, at 20 degrees Celsius is placed in between two flat plates, a distance h equals 0.1 meters apart. Since the viscosity of water has been previously determined experimentally at 20 degrees Celsius, its value of 1 millipascal seconds will be used. A Couette flow is generated when the top plate is pulled parallel to the surface of the fluid at a constant velocity of 12 meters per second, while the bottom plate is held stationary. As the top plate is pulled, a velocity gradient is established in the fluid and is visualized by the colored particles. At the bottom plate, the water is moving at a velocity of 0 meters per second, while at the top plate it is moving at 12 meters per second. This is due to the boundary conditions set in the problem. The no-slip boundary condition being used here forces the water in contact with the plates to be stuck to the plates. This means when the top plate moves, the water in contact with it moves too. The best way to model the velocity profile between the plates is using a straight line, u of y equals my plus b, since the velocity should be increasing linearly from the bottom plate to the top plate. Here, u of y is the velocity of the water moving in the x direction as a function of y. Y is the distance from the origin in the y direction, and both m and b are parameters we need to determine based on our boundary conditions. The first boundary condition we will use is that y equals 0 meters. Here, the velocity of the water equals 0 meters per second, since it is stuck to the stationary plate. If we plug these values in, we find that b equals 0 meters per second. We can rewrite our original equation, again setting b equal to 0, and obtain u of y equals m times y. Now, if we use the second boundary condition, that at y equals 0.1 meters, the velocity of the water equals 12 meters per second, we can plug these values in and obtain m equals 120 seconds to the negative 1 power. We now have both parameters, b and m, and can write the velocity profile of the water as u of y equals 120 seconds to the negative 1 power times y. Now that we have the velocity profile, we can calculate the shear stress. The shear stress is written as tau as a function of y equals mu times du by dy. Taking the derivative of our velocity profile with respect to y gives du by dy equals 120 seconds to the negative 1 power. Plugging du by dy along with the value 1 millipascal seconds for dynamic viscosity into the equation for shear stress yields tau as a function of y equals 120 millipascals. Since the variable y is not in the equation for shear stress, this means that the shear stress anywhere along the y-axis is 120 millipascals. However, this does leave one question. Which direction does the shear stress act in? To answer this, we need to look at the components of the viscous stress tensor. These are all of the components of the viscous stress tensor for isotropic materials. Here, the shear stresses are represented by the symbol tau, and the normal stresses are represented by sigma. These components describe the state of stress experienced by the infinitesimal cube when it is oriented with its faces normal to the x, y, and z axis. If we look closely at the stress components, they are all functions of at least two components of the fluid's velocity. The velocity components u, v, and w correspond to the x, y, and z directions respectively. However, at the moment, we are only concerned with fluids flowing in one direction. In our example, the fluid only has a velocity component in the x direction, which is given by the function u of y. As a result, many of these stress components reduce to zero, leaving only two shear stress components. Remember, the function u depended only on the variable y, so only stress components that contain the partial derivative of u with respect to y are retained. The direction these two shear stress components act in is given by their indices. Remember that the first index indicates which face the stress acts on, while the second index indicates the direction the stress acts in. This means we have a total of 4 shear stresses acting on our infinitesimal cube. One from tau xy on the positive x face acting in the positive y direction, and one from tau yx on the positive y face acting in the positive x direction. The shear stresses on the negative x and negative y faces are equal and opposite to the shear stresses on the positive sides to maintain equilibrium. Going back to the problem, the shear stress as a function of y, denoted as tau of y, is a constant value, 120 millipascals. This means if we place the infinitesimal cube anywhere along the y-axis in the fluid, the state of stress will be as shown on the cubic element. If shear stress was a function of y, then this would not be the case, and shear stress would change along the y-axis.